Afternoon. It's great to see you're all so awake. Hopefully this will be really exciting. It's going to be a little short. I understand I'll have more time tomorrow. But it's about the elements. And to start out, this is a picture of a lot of the elements. It's by no means all of them. There's 92 stable elements of 118 total elements. But if you look at this picture, you see something kind of odd. They're almost all metals. You can see one little vial up there with some brown gas, but I think everything else on here is metals. And the question would be why? Why would there be so many metals and very few nonmetals? If we look at the periodic table, down on the bottom rows you can see some of them are black. Those are synthetic elements made by humans. And they don't have any kind of a lifetime. They exist for very, very short periods of time. So we'll ignore those. They're really not even real. They're not from nature. And then if you look over on the far right column, you'll see what's called the inert elements, or the noble gases. And those elements don't mix with anything. They're kind of very unique. The red ones are the non-metals, and there's only, I think, 8 or 9 of those that are not metal. And then all the rest of the elements on the table are metals. So this theory attempts to explain the structure of the nucleus of the atom as coming from chemistry. Why is the periodic table as it is? Now, you might wonder where the elements are created, and fortunately, we happen to know. If we look here, we have different colors, and at the top, you'll see everything that's blue is made in the Big Bang, back at the very beginning of the universe. We have the green ones. They were made in dying low-mass stars. The yellow ones are exploding massive stars. The cosmic ray fission is kind of the pinkish. Merging neutron stars, and we all love neutron stars, are all purple. And exploding white dwarfs. So all of these are extremely high pressure, high temperature, and very, very unique environments, and they do not exist here on the planet. So the conventional belief is that elements are only changed into different elements in this type of a high pressure, high temperature environment. What I'm going to talk about today is a whole different theory that gets into different ideas about this, and that is the nucleus of the atom actually structured? And conventional science would say, no, we don't know of a structure, and that there's improbabilities and uncertainties, and things are moving in and out, and they're changing and swapping places, and we will never understand a structure except through mathematics. The nucleus is thought to be very, very chaotic in nature. In addition, it takes 3 forces to hold a nucleus or an atom together. One, you need the electrostatic force, which holds the electrons to the nucleus. And then there's these 2 strange forces called the strong and the weak force that hold the nucleus together. And in addition, the conventional belief is that the neutron is a fundamental particle, and that's probably not quite the right word, but we also know that even though it's supposedly a particle, it decays into 2 other particles. So how can you have a basic fundamental particle that conveys into other basic fundamental particles? That seems kind of contradicting. This theory, on the other hand, the structured atom model, says that there is a structure. And this structure, it grows very predictably, or as the elements get bigger and bigger. And that structure determines the properties of the elements. And it actually, because it determines the properties of the elements, the reason the periodic table looks the way it does is because the structure grows in the way it does. It's also easy to understand. I have here some magnets. And I can teach every one of these kids out here how to build the carbon atom. This is thought to be the carbon atom. And then within 5 minutes, they could be building even larger atoms. They can hold it in their hand. They can see how it works. They can see this is a very compact, very strong shape here. And so it's something that you don't have to have a PhD in physics or mathematics in order to understand. It also only involves one force, and this has been mentioned many times by other people today, is that there is no strong or weak force. There's one force that holds the atom together, and that's electricity, or the electrostatic force. So we have a little bit different interpretation of the neutron, and I'll be getting into that a little bit more in more detail shortly. So what we have here is 3 different branches of science. We have particle physics, nuclear physics, and chemistry. And chemistry is what we're used to. Chemistry is when you burn a candle, or you eat food and it breaks down and turns into some type of energy. or cooking an egg, or rusting iron. All these things are chemical reactions. And a chemical reaction is when you take and you reorganize elements. So you start with, say, two oxygens and a hydrogen, and you make water. You didn't get rid of the oxygen, you didn't get rid of the hydrogen, you still have the same number of hydrogen and oxygen atoms. They've just combined together differently, and that's a chemical reaction. And these are relatively low energy reactions, even though TNT or things like that seem to put out a lot of energy. It's still very, very low energy compared to nuclear reactions. Nuclear reactions are used in our nuclear reactors, such as fission reactors, and we're desperately trying to create fusion reactors. These put out many, many, many times more power than a chemical reaction would. So if you were to, say, a fission reactor breaks uranium down into smaller elements, and it can put 1,000,000 times out more energy than a chemical reaction. So you can have a small amount of maybe this much uranium in weight, and it's equal to carloads of coal in energy, or train carloads. Then on the left, we have quantum mechanics. Now, these are the people that like to take atoms and smash them together at high speed and break the atom into little pieces. And then they look at the little pieces and they try to put them back together again and create oxygen. To me, this is a little bit odd way to go about science, in that if I were to take an F-15 and a locomotive and ram them together and then look at the pieces, what do you have? So we're not going to worry about the left side. This is what most people, when they try to create a model for the atom, they try to understand is all these little quarks and leptons and gluons and fermions, and there's over 200 now, I think, part of subatomic particles. And we're just going to ignore that whole part. It has nothing to do with this theory. This theory is based on chemistry, and it's over on the right side of the chart. So the green line shows us what we're going to be talking about. So this is just a table of contents showing the things I'll cover, some history, some things that it's based on, what we've called the pillars of evidence, the theory itself, and then what's the point of knowing all of this? And that gets into the transmutation, which you've heard that word many times today. This is the gentleman that has created this theory. His name's Ito Call. You've probably seen him wandering around. He's been working on the theory for 13 years now. And he started with very simple exploration of how do marbles fit together? What kind of structures can you make with them? And at one point he came up with what he thought was the third element of the periodic table, and that's lithium. And he realized this was a very unique and important shape, and that he'd maybe stumbled onto something. He then went on to beryllium and boron and carbon. Eventually he grew into larger and larger atoms, and in 2016 presented at the Electric Universe Conference in Phoenix. And that was when I met him, and I was actually well, I'll get into that slide just a second. And you can see we've gone on now for the last 3 years working together. Here's a picture of us sitting on the curb of the Geology Museum at the Grand Canyon. And this is actually the first time we really talked. It was a 120-degree day. We're on a geology tour. I asked him about his model. He pulls out his backpack and 3 notebooks and starts flipping. Of course, everyone has 3 notebooks at the Grand Canyon. Starts flipping through his notebooks, and I realized, looking at his data, that he had not started this theory last week. He had thousands of hours into it, and that there were all kinds of correlations. He had shown how his structure creates the elements and creates and defines the shape of the periodic table. And then I joined him. I started a week later writing software to help demonstrate his theory. So just really briefly, the atom is thought to be composed of 3 different particles: the neutron, the proton, and the electron. The red and green are the neutrons and protons, and that's the nucleus of the atom. And surrounded by it, in the little picture to the left of all the electrons going around, those are electrons around the nucleus. Now, the nucleus is teeny, teeny, tiny. It's itty-bitty compared to the size of the atom. And it says over here, the nucleus, were the size of a raisin, the atom would be larger, or the electrons would be around the edge of the football stadium. So the nucleus is very small compared to the entire atom. Now, those electrons, we've pretty much figured out how they move around the nucleus, and we have all this shell stuff. And I just show, if you guys are familiar with chemistry, you'll know what I mean at the bottom. But that's how they understand chemistry, is through what the electrons do. Now, chemists don't care about the nucleus. They just care about the electrons. And they think chemistry really is based on where the electrons are. Nuclear physicists, on the other hand, really don't care much about the electrons. They worry about the nucleus, and the nuclear physicists are in the west wing, and the chemists are in the east wing. And it was really amazing. We went to a conference, and they were shocked to think that possibly the nucleus has something to do with chemistry. So SAM is based on some very, very basic principles. This isn't advanced math. This is just really basic ideas. And I'll go through these in a little more detail here. I'm kind of limited on time, so I'll just skip over this right now and show you the detail. And the first concept is duality. So you've all heard of yin and yang. So everything is broken down into two different extremes of one idea. If you think about, for example, temperature, there is no such thing as hot, and that's completely separate and different from cold. Instead, what we have is something called, it's believed to be motion. I've heard several people tell me it's really not even motion. But there's one principle behind it, and then there's the extreme end is cold, another end is hot, but they're really the same thing. They're not separate and different ideas. And so we have the idea the electron and the proton are completely different ideas. They're incompatible, or they're not incompatible, but they're two different things. And I'd like to put forth that it's one thing with two different extremes to it. And the proton is thought to be hard, it's physical, it's structural, and it builds things. But the electron, when scientists, physicists speak of the electron, they generally speak of the electron as being more of a wave. They very seldom speak of the electron as being a particle. So once again, this is a duality. We have the physical proton and the non-physical ethereal electron, or wave. So that's a basic principle of this theory. Now, as I said, Ito started with basically combining marbles initially together to see what he could build. He tried cylinders and different shapes and circles, and he found out that some of them are weak and they fall apart, and some of them are very strong. He eventually graduated into magnets like these. And this was really kind of a breaking point, or not it really shifted everything because it made it a lot easier. Taping things together and gluing wasn't that convenient. So these are actually, the magnets are the masters of how to put things together. They will teach you. And what happens when the magnets come together is that they create a dense packing. They arrange themselves in such a way that they don't roll and they don't fall apart. Now, typically, when people talk about dense packing, it's this idea that you see with the oranges, where you're trying to stack something on a table, or you're trying to stack cannonballs so they won't roll around. But if you look at the oranges, you can see on the sides it's threes, it's triangles. But if you were to look up from the bottom, you'd see that it's a square. And the square means that they are not nested together tightly, they're stacked in a way. And this is not actually a very strong shape. In playing with the marbles, you'll find out that is not a strong shape, to have things stacked on top of each other, or side by side. And so Ito came up with an idea that when I went online, he told me about his theory, and I figured I'd Google how to put things together in the way he thinks, and I found absolutely nothing on the web. He said he thought that they have to be densely packed, and there's a central force somehow holding them together. So instead of gravity pulling them down like oranges are pulled down onto the table, there's a central force pulling them to the center. And so we call that spherical dense packing. And the result is this right here, the icosahedron. The Platonic solids have fascinated man for a long, long time. And they're actually named from Plato. You can see here some examples of different people. The artists really love the Platonic solids and have done a lot of work with them. If we look a little closer, we'll find out there's 5 Platonic solids. And each one of these, if you were to put a sphere around it, you'd find that each of the marbles touch the edge of the sphere. So they in a sense, create a sphere. The first one is the tetrahedron in green. It has 4 sides and 4 vertices, and it makes triangles. So that's good. That's a good thing. The cube, on the other hand, in the pinkish, is, once again, they're stacked side by side, and that's a weak shape. You could just squish it, no problem. The octahedron also makes triangles. It's in yellow, or not, yeah, octahedron in yellow makes triangles. But once again, if you see, it's really based on 4. It's based on the square. And even though it has the triangles, and it appears to be densely packed, it's still not that strong of a shape. The red one is the icosahedron, which I have here. And it is the largest solid you can get with this idea of dense packing, of the spherical dense packing. And then the final one is the dodecahedron in blue. It's got a lot of empty space. You can't even build it with magnets. It's structurally unsound. I'm just going to skip this one really quick. So what he did was he found lithium. And lithium is kind of a partial icosahedron. If you see the ring of 5 in there, and then it's got 2 spheres on each side, that's lithium. If I were to make 2 rings of 5 and nest them together and put 2 spheres on, I would get icosahedrons. So the lithium is really a partially built icosahedron. So when we go from lithium-6, you can see it's partial. It's like the ring of 5 isn't complete, whereas in the lithium-7, it completes it. And you would think that the elements would go 1, 2, or in even numbers, 2, 4, 6, 8, for the number of spheres, or nucleons as they're called. But it turns out lithium prefers to have 7, an odd number, and lithium-6 is much less abundant. So if we continue to grow, if I'm going from lithium-6 to 7, I add 1 more, I get lithium-7, that's the pink one. I add 2 more, I'm building onto it, I get the beryllium. I add 1 more, I get boron-10. Now boron-10 is once again an even number. You'd think the elements would follow this idea that you have an even number of nucleons, but you can see it's incomplete. So I think the percentage is about 3 or 4% for boron-9 or 10, and then all the rest, the 92%, is boron-11. And finally, we add the last one on carbon-12, and we get the icosahedron. Again, and that is thought. Now, if you think about all of organic chemistry is based on carbon, and carbon seems to be an extremely key element, and it just makes sense that it would be the largest building block that atoms are made from. Now, one of the basic principles of the structured atom model is that it follows the periodic table, and a key idea of the periodic table is something called valence. And when you combine, if you look at the very bottom and we see fluorine, we combine hydrogen, 1 hydrogen and 1 fluorine, we get hydrogen fluoride, and so fluorine has what's called a valence of 1. Oxygen, on the other hand, likes to have 2 hydrogens, or -1. Oxygen has 2 hydrogens and is a -2. Nitrogen, which is NH3, has 3 hydrogens, and carbon has 4 hydrogens. So this progression of 1, 2, 3, 4, -4, -3, 2, 1, 0 is actually called the law of the octaves. It was discovered a couple centuries ago, and it was one of the first ideas that eventually resulted in the periodic table. And this law of the octaves principle is determined by how this grows. And the little bit more complex theory about valence is something called oxidation states. So this is more sophisticated, but it still includes valence as a basic base to it. And I can't go into a lot of detail on it, but if you look at the left, we start with the lightest elements at the top and go to the heaviest elements at the bottom. And you can see this diamond shape in how the oxidation states change. And so this is very complicated. We got some every other things. We got diamonds. We got things that seem to just stop. It seems like something very complex is going on here in order to create this pattern in the elements of the oxidation states. So in working with valence, Ito came up with what he called the structured atom model. And this model had to fit what we observe in the periodic table, or he threw it out. He's no making up new particles, no creating new forces. It had to fit. And the first concept is the neutron. Now the neutron, we know from science, within 15 minutes, if it's pulled out of the nucleus of the atom, will decay, or 15 to 18 minutes, will decay into a proton and electron. And this thing called an electron antineutrino. So once again, if the proton and electron are basic particles, how can they be derived? How can the neutron be a basic particle and yet break into 2 more? the neutron must be inside an atom to stay together. So you think of this, that there's a particle that can't exist by itself. That really doesn't make sense. So Sam redefines the neutron to be a proton and an electron, which it is, but the electron is shared with other protons. The reason they discovered the neutron, this is a discovery in science. In 1933, Wolfgang Pauli was trying to solve an equation where they had spin problems. And if you add the spins up, it doesn't make sense. A half plus a half does not equal a half. And so what they did, he created an anti-electron neutrino. He discovered the anti-electron neutrino. And he gave it just the right properties he needed. It has no mass, it has no charge, it has no volume, it doesn't have anything, but just exactly the right amount of spin to solve the equation. And there's another gentleman by the name of Carl Johnson who goes through very clearly explaining that what really is going on here is that they made a mistake in their math. They're using scalar mathematics instead of vector mathematics. And when you use vector mathematics, the spin comes out, you don't need a neutrino. But this neutrino is pretty magical, let me tell you. We have all these different types of neutrinos. We have flavors, we got types. It may have mass, it might not have mass, it might have extra heavy mass. It has different states. So literally, if you got a mathematical equation and you can't solve it, what you do is you stick a neutrino in there. And if the neutrino doesn't have the right properties, well, you give it a new property. And you get a Nobel. So this type of science, I love this quote by Mark Twain, in the space of 176 years, the Mississippi has shortened itself 242 miles. Therefore, in the old Silurian period, I'm not sure when that was, the Mississippi was upward of 1,300,000 miles long. 742 years from now, the Mississippi will only be 1 3/4 miles long. So there is something fascinating about science. One gets such wholesome returns of conjecture out of such a trifling investment of fact. And on that, well, no, I'll do one more slide. No, I'm going to leave it right there. Tomorrow we will take this on further and I'll get more time. So, thank you.